of course, going for lead and other things.
The philosopher's stone.
They were introducing impure substances to make gold.
Yeah.
And they were thinking that that gold could be produced, but that could only be if the affinities of one or the other could join. Lead could be used, yes, but not in the same manner as they were thinking.
Yeah.
Mercury could be used, but they had no affinity. That would form an amalgam. So that's where he was frustrated. The alchemists were frustrated, Boyle's law, and he said that, well, I don't know, I cannot find any similarity.
So let's see, now you're talking about, it's possible to estimate the affinity of the force from the force of attraction between two masses, M1 and M2, to be directly proportional to their product and inversely proportional to the square of their separation. So here you're looking at Coulomb's law, and this is the force of attraction between mass 1 and mass 2 is, say, a positive charged particle, negative charged particle, and the force inversely proportional to the radius squared. So you can learn this from your PhD studies.
This is the species, the square of this separation. You see, the force, of course, is related to mass and the
So
amount of separation.
This gave you an idea that a loose model for social affinities. For example, if a mass, say mass 1, when you were separated from your family in Canada, the radius was increased. So there's less force of affinity. Is that correct?
Yeah, the force is coming together. Is coming together and separation.
Mm-hmm.
The attractive forces and the repulsive forces, they are controlled by FA.
Mm-hmm.
The force is controlling the mass of mass 1 and mass 2 by maintaining a distance,
Okay.
by reducing the distance. If the distance is reduced, there is cohesion. If the cohesion is not possible, and if the cohesion is not there, in that case it will be separation.
So, for example, in this point
this
here,
explains it.
you say in equation 5.2, which is this equation, we're talking about, this is 5.2, you're talking about the radius of separation.
The distance that I was explaining here.
So you say down here
Yeah.
that the
The
denominator,
is important.
because estimating the affinity, because it is related to the distance, the closer the relation, the higher is the affinity.
Higher.
However, when such persons come so close that there's a clash of interests, or when the zone of their command overlaps, there's a mutual repulsion, and the affinity is decreased. They have to be warned to maintain a distance. And you say this is similar to the case of ions, for example, sodium and chlorine ions in the lattice of sodium chloride. And then you go on here. When the ions are brought so close together, there is electron cloud overlap in the negative way, and there's a mutual repulsion involved. And then you say this model applies to social examples too. That's a good. Let's see on page 99. You see here. This here I have a question about. From here to here, you say about this affinity scale is money. So Pakistani society has been mentioned earlier as being heterogeneous and comprises city dwellers, agriculturists, and tribesmen. You say the fugacity of each category is different. For the first two categories of workers, dwellers and agriculturists, the affinity is the main term, the main affinity scale is money. And then the last one, the tribesmen have different affinity scale. What do you mean by this? So you say these two have one, the dwellers and the agriculturists have one affinity scale, and then you say the tribesmen have a different affinity scale. What do you mean by this? So you're just saying that pretty much the attraction of a person to a certain company was measured by the money causes the force of the draw of the lure to the job, something like this. Like the more the city dwellers have high affinity for the city because they make more money, something like this. The high pay of job forces the people to the city to make money, but the other ones, something like the agriculturists and the tribesmen are manual laborers who lead a harsh life and working desperately to earn and return home with expected riches. Something like this. I guess I see what you're saying. Let's see what else we got here. Affinity scale. And now we're going to get to this page 100. 101. So now we're talking about free energy changes. That's the delta G. So now, in order to understand the behavior of an individual in a society and interpretation in terms of his likes and dislikes.
Before we go here, there is another one in between the city dwellers and the rural workers. There is a feudal lord.
Feudal lord.
Yeah. The feudal lord has hold on the people who have settled in the urban area as the kings of the landlord. So that is a different breed, and they are trying to control the other city dwellers who are earning their way, either earning their livelihood, either by factories, owning factories, or owning the real estate or businesses like that. Now, the conflict may be here between the city dweller and the agriculture in terms of living, but the conflict is also there because the city dwellers are not used to the type of interaction or cooperation that the landlord may exert on their people. So there is a conflict between those people and the agriculturists, the agriculture. The group representing the agriculturists and the group that is earning a hardware through their own means.
Okay. When I go back home, I'm going to listen to what you said. This is my favorite part right here, the free energy changes. Let's see here.
In terms of likes and dislikes of there's a component codified by whose secondary insertion then into a form.
So right here you say,
and we explain that in terms of that beaker,
yeah.
2 beakers.
So now the understanding of chemical reactions in terms of free energy changes is now well established, which we've just talked about, and in trying the interpretation of human behavior with respect to physical phenomena would be pertinent to describe the laws of chemical combination.
Yeah.
So now we're going to go here. The true measure of chemical affinities is obtained from the changes in the free energy. which is the driving force of the reaction. So that's what we just talked about. So a system having two species A and
We
B,
talked about that.
yep, said to be in equilibrium, to yield C and D, forward and inverse reaction. And then we talked about, do you want to say anything about the law of mass action of Gutenberg and Wage in terms of social application?
Yeah.
What?
This is an important reaction because everything, the reactions depend not only on the temperature and pressure, but also on concentration. So there are three constraints in the phase rule. One is temperature, the other is concentration, and the third is the pressure.
Yeah.
Now, A plus A, B plus B may be equal to C DD, concentration of C and concentration of D, where A and B are powders and solid. This law shows that chemical affinity depends on the chemical nature of the species and on the concentration and the specific conditions.
Okay, how about in the case where we have A and B is reacting on this side, CD in this reaction, and say you have, can you explain this in terms of how about the concentration of the Afghan migrants into Pakistan?
They can interact. They can interact to form CC and DD under ideal conditions of temperature and pressure.
So how about with the
And
case?
also concentration.
Okay, so let's look at concentration. Let's say you have a social system and you start adding more and more migrants into the system and the concentration increases. How does that shift the equilibrium in terms of Gutenberg and Wage, law of mass action?
The concentration certainly has a meaning because if there is pressure, in that case they will coalesce, and in the case of temperature, they will separate out. So C and AABB may form CC and DD only under certain conditions.
Okay.
Conditions of temperature, pressure, and also concentration.
This quote I thought was pretty good. So he said in system 5.4 here, that the equation 5.4, the system is said to be in equilibrium if the free energy change or driving force is zero. No net work is accordingly obtained. It may be mentioned that the equilibrium condition does not imply cessation of all activity, but indicates status quo. So in this case, there's forward and backwards reaction, and this is like a status quo society that's still operating, and it's in equilibrium, and there's no driving force is zero, but does not imply cessation of all activities. That's very important because a lot of people believe that equilibrium means heat death, and that means cessation of all activities. So now we see that from a chemical point of view, it does not mean cessation of all activities. It just means status quo.
The equilibrium condition is changing.
Yeah.
The equilibrium condition is changing under those three conditions.
Mm-hmm.
If there is too much of concentration, or thinning out in concentration, if there is too much of pressure or lack of pressure, vacuum, in case of temperature, whether it is cool or temperature, or the temperature is increased. That means, in social terms, if there is commotion, can the commotion be controlled? And also, if there are too many people exerting on the social system. So the three of them can bring about equilibrium, yes, but that is a critical stage. In each case, there will be an equilibrium,
Okay.
but the equilibrium is unstable.
Unstable equilibrium.
Yeah.
But does not, the point here is that does not indicate cessation of all activity. There's still activity going on
Yeah.
at equilibrium, but it's just there's no forward progression.
Yeah.
There's no driving force.
Yeah, the driving force will change.
Okay, I'm going to show you.
Chemistry, the concentration temperature and pressure
Have you ever-
are the constants.
Okay, I'm gonna show you the example of somebody who disagrees with our point of view.
Okay.
Have you ever heard of Prigogine? He's a French, he's a Belgian, Russian-born Belgian chemist, and he was the guy who promoted the thermodynamic theory of far from equilibrium theory, of dissipative structure theory, according to what that life's life is something that's far from equilibrium. It's not at equilibrium, and he says. Okay, so he won the Nobel Prize for this dissipative structure theory in 1977, and he said that human beings are what he called dissipative structures, and that he got the idea from what are called Bernard cells. If you take a plate of whale oil and about that's this thick, and you put flame underneath it, first it's just a liquid mixture. There's no kind of ordered structure. But if you start heating it long enough, when it gets to a certain Reynolds number, it forms these hexagonal shapes in the liquid. So he says that heating a system from the equilibrium state to the far from equilibrium state, when the heat flow starts increasing, it forms these ordered structures. And he says this is the model for humans, and that because we're dissipative structures. So his theory was very in vogue or popular from 1970 up till about the 2005. Now nobody follows it anymore, but for a certain number of years, people believe this. And he said this during his Nobel Prize speech, this quote here. He says that the thermodynamic equilibrium may be characterized by the Helmholtz free energy, F is equal to E minus Ts. And then he says, are most types of organizations around us of this nature? He said, it is enough to ask such a question to see that the answer is negative. He says this does not explain the order of structures we see. So he disagrees with our point of view. He says, obviously in a town, a living system, we have a quite different type of functional order. To obtain a thermodynamic theory for this type of structure, we have to show that non-equilibrium may be a source of order. Irreversible processes may lead to new types of dynamic states of matter, which I've called dissipative structure. So he's saying that in your last quote here, when you said that at equilibrium, it does not apply cessation of all activity. There's still ordered structure going on, but it just means there's no driving force. So he says that the free energy equation does not explain the functional order of a town. So what is your opinion about this?
Mm-hmm.
You say he's correct, he's incorrect, right?
You know, to ask for the answer, say the answer is obviously in a town, in a living system, we have quite a different to obtain a thermodynamic theory for this type of structure. We have to show that there is non-equilibrium may be a source of order. Irreversible processes may lead to a new type of dynamic states of matter, which I have called dissipative structures. He is right.
Huh?
Yeah, he is right. Because this is in a thermodynamic equilibrium. The equilibrium in thermodynamic sense is always unstable. You achieve stable. You do not achieve a stable equilibrium in any case. It is always shifting because of the constraints.
Mm-hmm.
So when he says that it is enough to ask such a question, say that answer is negative. Because obviously in a town, in a living system, we have quite a different functional order. In our case, let us say it is the agriculturists and the town dwellers. So the equilibrium will be only a functional equilibrium introduced by a governance system.
Well, let's take a look at this. I think you don't understand what he's saying here. So he says that the thermodynamic, the free energy, the minimum of the free energy characterizes, he says the minimum of free energy does not characterize the organization of a town. So we've just shown in our last graph that we made here that the free energy, the final state, does characterize the formation of the new town. But he's saying this doesn't characterize it. He's not really saying it about equilibrium, but he says that this equation, the F equals E minus TS, does not apply to the formation of the ordered formation of a town. So in this last diagram, we said that the minimum is the well at the bottom, and that does characterize the ordered functional, the ordered structure of a town.
Look, Helmholtz free energy is related to constant pressure. You are maintaining a constant pressure.
Yeah.
In that case, things may be negative and positive in case of differences in pressure.
Yeah.
Constancy in pressure is not being maintained. So, since it is not being maintained, Helmholtz free energy law will not hold.
Okay, but how about Gibbs free energy?
It will be Gibbs energy.
Okay, so from your point of view, Gibbs free energy, the minimum of the Gibbs free energy
is the better one.
Okay.
Because constant pressure is not possible.
Okay.
Constant pressure is an outside force. It's an outside pressure.
Okay, but just
it's an external pressure.
Okay, you're correct. So the question I'm asking is, does the Gibbs free energy, the minimum of the Gibbs free energy, explain the organization of a town? That's correct, right?
It gives energy that is all pervasive.
Yeah.
But this constant pressure is
Yeah,
almost impossible.
you've got the right idea. Yeah, he's just a little confused. But back in the 1970s, he won the Nobel Prize, and everybody was like, "Oh, this is the new way to explain everything." Well, let's go back to your book here, and I'll keep moving. So now, the energy changes. So now we talked about Gutenberg and wage. Now we're going to talk about, just talked about this. Now we're going to go forward here. So now you're saying, just like I did, remember when I made my graph and I made these scales, that this is the more negative is the more spontaneous. So the most spontaneous reaction here is this reaction.
You have those theoretical figures, there are practical figures.
Yeah. So I use, these are, we both think the same.
But I like the way you have put it. Yes.
You're impressed.
Yes,
That's the only way I could figure it out.
You have to start from somewhere.
Yeah, start from somewhere.
You have to, this is practical. This is practically a step.
Yeah.
But then you have to start from somewhere.
Yeah.
And you took a start.
Yeah,
I was only thinking.
Yeah.
I did not have the means.
Uh-huh.
If I had the background, if I had all the information available, maybe I would have come to. But I was always thinking that something like that should be there.
Yeah.
And I found that you are doing it.
Yeah. Thank you, sir. You see?
I don't know how it is possible that the two of us we are working on the same way.
Yeah.
But you have taken a start.
Yeah.
I was still in the predecessor stage.
Yeah.
You are in the interpretative stage. Yes.
I'm in which state?
I acknowledge that.
You were in the metals table state, and I'm in the which state?
I'm in the predecessor stage.
And me?
You are interpretative stage.
The which stage?
Interpretation.
Interpretation stage.
Interpretation.
Okay. All right, let's see what we got here. We got this equation of 5.5. There are many ABs. There's just as many ABs being formed as there are dissociations in AB. This represents a society lacking a driving force, meaning thereby that is future instead of instead of being progressive, is only like its past. I like this good philosophy right here. Do you have a society, an example you could explain here? What would be an example of a historical society that was in?
Being formed as an association. Now we are at a stage when to discuss the association and dissociation.
Mm-hmm.
They are dissociated.
Uh-huh.
This is associated.
Mm-hmm.
Association and dissociation are interrelated.
Okay, but this right here you say, a society that lacks a driving force thereby lacks a future. So give me an example of a society where the forward reaction equals the backward reaction. In your mind, the real example in history.
Well, any heterogeneous society is like that.
Any society that's not progressing. Any society that lacks a driving force is living in the past.
Pakistan is a heterogeneous society. India is a heterogeneous society. But Myanmar gives us an example.
Who?
Myanmar, Burma,
Well,
the next to Bangladesh is Burma or
Burma.
Burma
They
or
lack
Myanmar.
Myanmar.
Yeah.
They lack a driving force.
Myanmar has either the Buddhists or the Muslims. The Muslims had their own state, Arakan. But they have almost been annihilated. So the interaction between them has started. They were a largely independent society, homogeneous society, let's say.
Here we go. Can you grab me one more Diet Pepsi, please? So we're going to look at this one here. We're going to take a look at this where you talk about the catalyst and platinum sponge, and I'm going to show you that Goethe did the same thing in his. Yeah. So let me get the Diet Coke first.
I was trying to tell you that H2 and water.
What?
H2 and oxygen.
Uh-huh.
H2 and half of oxygen making water. But they may coexist.
Uh-huh.
They coexist without forming water. Some catalyst has to be introduced. For example, if it is dry oxygen and dry hydrogen, nothing will happen.
Yeah. So
In case a drop of water water vapor is introduced, the reaction will be explosive.
yeah. So you say.
So it has to that equation of yours that needs a catalyst to be introduced in it.
So what you say.
They don't remain in equilibrium. The equilibrium has to be forced.
Okay.
So to the right side by a catalyst.
Okay. So Mirza here is saying that if you have dry oxygen and hydrogen, they won't react unless you add the catalyst of the platinum sponge. And the platinum sponge lowers the activation energy barrier, and that allows the reaction to occur. So now we're going to take a look at how Goethe did this in his novel. I'm going to look it up real fast. He called he did work on, he hired a chemist to come and actually